All right, paper 2 time. So I think most people did find this a bit easier, especially this question. If you revised a bit of vectors, this wasn't too bad. So we're told we got point A with a position vector 4, 5. 4 minus 5, sorry. And a point B with a position vector of minus 5, minus 2. So 2 points. If you want, you can sketch these. I guess we should do it accurately for the video. So we've got A, which is 4 minus 5. A and B, which is minus 5 minus 2. So not to scale. Okay, but in reality, you can sketch these any way you like. So if I just do a set of axes, any point A, any point B, they can have those coordinates if you want, but it doesn't really matter. First thing we need to do is find the vector A to B. A to B is always the same. To go from A to B, when we know the position of A and the position of B, we can just say AB is minus A plus B. So AB, as a rule, is OB minus OA. So if I put my vectors into that, we can say AB equals OB, so minus 5 minus 2, minus OA, which is 4 minus 5. Minus 5 take 4 is going to be minus 9. Minus 2 minus minus 5 is going to be 3. So vector AB is minus 9i plus 3j. Part B of this is find the size of the vector, or the modulus of the vector. So mod AB, which is the magnitude. So we use Pythagoras to basically find the size of this vector. So we're going to square the x or the I component, square the y or the j component, and square root them. So minus 9 squared plus 3 squared, which gives us a square root of 81 plus 27, which ends up simplifying as 3 root 10. Cool, so that's that one. Next one is kind of a proof, kind of an investigation that you have to do. So we're given one line and the coordinates for a second line, and we're trying to decide if they're parallel, perpendicular, or neither. So first thing, let's find out the gradients of both of these lines, because that's what determines if lines are parallel or perpendicular, what their gradients are. So line 1, 4y minus 3x equals 10. So to find the gradient of this, we can rearrange it into the form y equals mx plus c and read off the gradient. So I'm going to add the x onto the other side. So y mx c, divide by 4, and then we've got our gradient. So the gradient for this line, for L1, is 3 over 4. Let's write that down. L1 gradient is 3 over 4. Okay, L2. So we're actually going to have to find this one because we got 2 points. Now we don't even need to find the equation of the line. All we need to do is find the gradient of the line, because that's what will tell us if they're parallel or perpendicular. So to find the gradient, remember it's y2 minus y1 over x2 minus x1. So we're going to have 8 minus minus 1 over minus 1 minus 5. Make sure you get your x's and your y's the right way around, which gives us a gradient of 9 over minus 6, which will simplify to give us minus 3 over 2. So L2 gradient equals minus 3 over 2. Okay, so in order to decide whether they're parallel and perpendicular, we need to make sure these gradients are simplified as fully as they can be, and then we can look at them. Both of them are as simplified as they can be, so we can compare them. So if they were parallel, the gradients would be the same. These are not the same. So not parallel, as 3 over 4 does not equal minus 3 over 2. Cool. Perpendicular. The best way to check if gradients are perpendicular is to times them together and see if they equal minus 1. So 3 over 4 times minus 3 over 2 gives us minus 9 over 8, which is not quite 1. Sorry, minus 1. So gradients do not multiply to give -1, so not perpendicular. So we need to say, just to summarize, neither. Preferably in the lines if you're doing a real example. Next one then is you're looking at factor theorems, factors, and also transformations as well, really. So first bit, use the factor theorem. That's a key bit that some of you missed. Use the factor theorem to show that this is a factor of this. So the factor theorem states f of minus a equals 0 if x plus a is a factor. So if that's a factor of a function, subbing in minus a will make it 0. So to show it's a factor, we're going to sub in -2, because it's the opposite, into our function and show that it equals 0. So part A, g of -2 is 4 lots of -2 cubed, minus 12 lots of -2 squared, minus 15 lots of -2 plus 50. We can work our way through this. -2 cubed is going to be -8, so 4 lots of -8, minus 12 lots of 4, and then plus 30 plus 50, which would give us 0. So if you work all that out, we do get 0. So equals 0, therefore, probably do it properly, x plus 2 is a factor. Alright, part B. Hence show that g of x, the function, can be written in this form. So it's basically asking us to factorize our function. And the way we factorize cubics once we know a root is through long division. So I'm going to use long division to divide this cubic by this, and then we're going to factorize it to end up hopefully with this quadratic. So 4x cubed minus 12x squared plus 15x plus 50 divided by x plus 2. So x plus x is into 4x cubed, give 4x squared. So times to find the remainder. Subtract them, so we get minus 20x squared minus 15x plus 50. X is into minus 20x, go minus 20x, times it down, minus 20x squared minus 40x. Subtract those to check, so we get minus, no we don't, we get positive 25 plus 50, 25x plus 50. X is into 25, go at 25, times down again, 25x plus 50, remains 0. If at this stage you haven't found a remainder of 0, you've done something wrong, because we already proved that it was a factor. So we end up with this quadratic. So if we can fully factorize our function, we start off saying that the function is this times this. If we factorize this, we get 2x plus 5 squared. So it's a nice repeated root there for that one. So there's our function. Good. And that does correspond with our picture here. So we have one root at -2, and the other root, if I know something wrong here. Yeah, of course. One root at sorry, back here. That should be a minus. So one root at -2 and the other root at positive 5/2. So for the last bit of the question, use your answer to part B to deduce the values of x for these limits. So when is the function less than or equal to 0? Well, it's less than or equal to 0 here, and it's equal to 0 here. So we need to say for this one, g of x less than 0 or equal to 0 when x is less than or equal to -2, because any x value here is going to be negative, and that x value is 0, or x equals 5/2 because it equals 0 at that point. So you need both of those ranges. And the last bit, when is the function transformed equal to 0. So we need to work out what this transformation is. So it's inside the function, so it affects x, and it always does the opposite if it's inside. So instead of stretching x by 2, it's going to squash x by 2. In other words, it's going to half all of our x coordinates. We're going to find out when it equals 0. Well, it used to equal 0 when x was minus 2 or when x was 5 over 2, but we're squashing it together, so now it's going to be minus 1 and 5 over 4. Cool. Right, last question was trigonometry, which was mixed really how this went. So trigonometry, you have two trig equations to learn, which is tan theta equals sine theta over cos theta, and sine squared theta plus cos squared theta equals 1. So we're going to be using both of those in this first bit. So we're trying to show that this equation, which is a mix of all of our trig types, can be rewritten as this, which is in terms of one trig type. So first thing, to think about this, we need to get everything in terms of cos. So we can keep this cos like it is. We want to change all this stuff and turn it into cos somehow. So start off by writing tan as sine over cos. So there we go, I'm going to change tan into sine over cos. So 4 cos theta minus 1 equals 2 sine theta times sine theta over cos theta. So now we're going to expand this set of brackets and aim to change these signs into cosines. So 4 cos theta minus 1 equals 2 sine squared theta over cos theta. I can multiply both sides by cos theta to sort this fraction out. So we get 4 cos squared theta minus cos theta equals 2 sine squared theta. Then I can think of a way to change sine squared into cos squared and get a nice little quadratic to solve. So I'm going to use my other trig identity, sine squared plus cos squared is 1. And we can think about rearranging this to find out what sine squared is in terms of cos squared. So if I say sine squared theta equals 1 minus cos squared theta, so subtract this cos squared from each side, we can put that in as sine and then solve it. So this will become 4 cos squared theta minus cos theta equals 2, 1 minus cos squared theta, like that. Expand this bracket, get it all on one side, and we've got a quadratic to solve. So some rearranging, you get to this quadratic. Now you can solve this on a calculator, or you can factorize it and think about what the factors might be. I'm going to cheat and save some time and just write down the answer. So we get 3 cos theta. Oh, actually, we don't even need to do that. I'm rushing ahead. So that is this part of the question done. Good. Okay, so now we need to solve this. Now, the astute students among you will realize this is the same as this, but instead of theta, we've now got 3x. We can imagine it's 3 theta. So we're going to need to solve it like normal, but we're going to need to stretch our limits, and we're going to need to divide our final answers by 3 in order to find x. So if we factorize our quadratic from part A, which we got here, we're going to get 3 cos theta, what's it going to be, minus 2, and 2 cos theta plus 1. So just double check that. 2 times 3 is 6 cos squared, minus 4 cos plus 3 cos, which gives us minus cos, minus 2 times 1, minus 2. There we go. So 2 sets of different things to solve. We're going to get cos theta equals 3 over 2, and cos theta is minus a half. So now we're going to find our principal values. So we need, oh wait, first of all, we've got to stretch. So yeah, we're looking for 3x instead of x, or 3 theta instead of theta. So we can write these as cos of 3x equals 3 over 2, and cos of 3x equals minus a half. Our original limits were 0 to 90, so we're going to need to stretch those by 3. So we're going to get 0 to 3x to 270 degrees. Right, now let's find our principal values. So 3x equals cos to the minus 1 of 3 over 2. 3x equals cos to the minus 1 of minus a half, which gives us our principal values. I'll work this out in the calculator. Cos to the minus 1 of this fraction amount 3 over 2 gives us, what have I done? 2/3. Cos to the minus 1 of 2 over 3. It has been a long day. 2 over 3 gives us principal value of 48.2. Remember, that's our 3x value, not x. And same over here, 3x equals inverse cos of minus a half, which gives us 120 degrees. So these are our two principal values. So we're going to sketch both of these on a cosine graph and find all the values between 0 and 270. So first of all, 48.2 is going to be about here. And we can see there's going to be another value over here. Now, the thing people keep doing wrong with this is where to measure from. For cosine, this 48 has been measured from 0, which is the peak. So we need to measure 48 away from this peak. So make sure you're always measuring from the same way. Easy way to track that is put arrows. So this one's measured from that peak. So this one needs to be measured from this peak. So in other words, we're going to do 360 minus 48.2 to find that value. And we're going to add it to our list. So down here, let's start the list. 3x is 48.2. It's now going to be 360, take 48.2, which is 311.8. But that's bust. It's already outside our limits, so not going to get that. Right, next one, 120 degrees. Well, 90 is here, 180 is here, so 120 can be about here. And we're going to get two values. Again, this is less than 270, so these are both going to count. And 120 degrees is again measured from the peak. So from here out, so we need to do 360, take it to find this one. So 120, and then 360, take 120, which is 240. We're going to divide these by 3 to find x, and then we're done. So x equals 16.1 degrees, it equals 40 degrees, and it equals 80 degrees. And we can check these right by putting them back into our original equation and checking if they do in fact equal 0. Cool, that's it. Cheers.